Hi children, welcome. Welcome to another class. In this class, we are discussing the first chapter of second year topic, that is solid state chemistry. Crystallography, that is our discussion in the class. Okay, let's go through a rapid revision on through the chapter solid state. Fine. See, first point, you need to have a distinction between the three different states of matter: solid, liquid, and gas. What are the characteristic differences between solid, liquid, and gas? You are learning in the lower classes itself. In solid state, the particles are closely packed, while in liquid state, they are far apart and the intermolecular distance is maximum in the gaseous state. So, number one, regarding interparticle distance. Distance is minimum in the solid state, maximum in the gaseous state. Okay. Second point, molecular force of attraction. Molecular force of attraction, as all of you know, it is maximum in the solid state and minimum in the gaseous state. So, interparticle distance, intermolecular forces of attraction. Then, regarding shape, volume, etc., all of you know, solids have definite mass, liquids have definite mass, gases have definite mass, solids have definite surface, definite shape. Liquids has a surface, but not a definite surface. It doesn't have a definite shape. It has the shape of the containing vessel. While gases does not have a surface, does not have a shape. Regarding volume, solids have a definite volume, liquids have a definite volume, gaseous matter has the volume of the containing vessel. So regarding shape, volume, mass, all of you know. Regarding particle distance, all of you know. Regarding molecular force of attraction, all of you know, right? What about the thermal energy? Thermal energy for solid, liquid, and gas. Thermal energy is maximum for gaseous state and minimum for solid state. If you compare an identical matter in the three different forms of their states, ice, liquid water, and water vapor, you know the thermal energy is maximum for gaseous state and minimum for solid state. Okay. Then what about the entropy? How comes the entropy? Entropy minimum in the solid state and a maximum in the gaseous state. So all these points can be correlated, understanding the characteristics of the three important physical state of matter. Even though there are 7-8 physical forms of matter science is dealing with, we don't have to proceed with that. The most commonly experiencing and practicing three important states of matter I am referring. That is point number one from the chapter. And of course, our discussion is mainly concentrating on solid state. Right? All of you know, solid matter has categorized into two categories. What are the two categories in the solid state? Solids are categorized into true solids, that is called crystalline, and amorphous. Crystalline and amorphous. Crystalline solids are called true solids, while amorphous solids are called pseudo solids. They are supercooled liquids. Crystalline solids are true solids. Amorphous solids are pseudo solids. They are supercooled liquids. They are highly viscous. For example, glass. Glass is amorphous in nature and that is a pseudo solid. Glass is highly viscous, that it resembles the property of solids. Okay. While true solids are crystalline in nature. How to understand the crystalline amorphous materials? The prime point of noting to be noted is regarding the arrangement of fundamental particles. The fundamental particles arranged in a regular repeating pattern. That is the point regarding crystalline material. In crystalline materials, the fundamental particles, atoms, molecules, ions, etc., arranged in a regular, repeated, ordered manner. That is crystalline, while in amorphous, they don't have a regular, repeated, ordered manner in case of amorphous materials are concerned, right? Crystalline materials will have a sharp melting point. Crystalline materials will have a sharp melting point, while amorphous materials will go for a melting point range. Okay, crystalline materials will go for a clean cleavage. Suppose we cut the object in a plane, it will give a clean cut. Is going to cut through a plane and is giving a clean cleavage, clean cut. While amorphous materials are not going to give you a clean cut, it will give you a irregular cut. So melting point will be sharp in nature. They have the fundamental particles arranged in a regular ordered pattern. They give a clean cut, while it is not observed in case of amorphous materials, right? Crystalline materials maintain long range order and short range order. There is long range order as well as short range order, while amorphous materials only maintaining a short range order. They have only short range order. What does that mean? What does that mean? Suppose we analyze two solids, and if we find a microstructure analyzed for two solids, one solid we are analyzing a microstructure, we find there is a particular pattern. We find there is a particular pattern. While if you take another solid, when you analyze a micro area, you find a particular pattern. Just imagine, you find a particular pattern, and wrongly we may be commenting both are crystalline. There is a regular pattern observed in a micro area, but crystalline materials, this arrangement will be repeating throughout in the solid. While amorphous material, you find an order here, but that is not repeating throughout. This is called a short range order. There is an order, but only in a short range. There is an order which is the short range order found to be repeating all throughout the material. So crystalline materials maintain short range order as well as long range order. While amorphous materials, there can be an order, but it will be a short range order, right? A very important property all of you know, crystalline materials are anisotropic in nature. They are anisotropic in nature, while amorphous materials are isotropic in nature. Isotropy, anisotropy. What is meant by isotropy, anisotropy? Maybe you are remembering. In crystalline materials, when the various physical properties observed from different directions giving different values, that is anisotropy. While isotropy means various physical properties, for example, thermal expansion. Thermal expansion observed in a solid from different directions. Thermal expansion observed in a solid. From this direction, you get a value A. From this direction, you get a value B. From this direction, you get a value C. That is called anisotropy, property of crystalline solids. While amorphous solids, when you take an amorphous solid, if you try to observe the thermal expansion from this direction, you get a value X. From this direction, you get invariably same value X. From this direction, you get invariably same value X. That is called iso. Iso means same. Isotropy. So various physical properties observed from different directions giving same value, that is called isotropy. Giving different value called anisotropy. Crystalline materials except some symmetric crystals. Some symmetric crystals like cubic systems. Not all. If it is perfectly symmetric, it may be isotropic. Otherwise, normally a general categorization for crystalline materials is anisotropy. They are anisotropic in nature, while amorphous materials are isotropic in nature. Similarly, enthalpy values, enthalpy of fusion, something like that, there will be a characteristic value for crystalline materials. We can't expect that for amorphous material. These are the characteristic differences between the true solids, crystalline and amorphous. Basically, what is the difference? In crystalline materials, the fundamental particles are arranged in a regular, repeated, ordered manner. While amorphous, it is not like that. Crystalline maintain anisotropy, amorphous maintain isotropy. Crystalline maintain long range, short range order, amorphous material maintain short range order. Crystallines give a clean cleavage, amorphous giving a irregular cut. These are the points concerned to crystalline and amorphous. No doubt, our discussion is mainly on crystalline region, right? Now, the next point of discussion happening in the chapter is types of solids. Types of solids. Types of solids. Mainly, we are learning four important types of solids. One is called ionic solids. Second one is called covalent solids or called network solids. Third one called molecular solids. And the fourth one called metallic solids. Metallic solids. So, ionic solids, covalent solids, molecular solids, metallic solids. What about ionic solids? First one is ionic solids. What about ionic solids? For ionic solids, the fundamental particles are ions. The fundamental particles are ions. For example, NaCl. It is cation anion arranged in a regular repeated order. That is called ionic solids. And the force of attraction will be ionic bond, electrovalent bond, electrostatic forces of attraction. They are generally found to be hard, brittle, and they don't conduct electricity in the solid state, but conduct electricity either in the molten state or in aqueous solution. And they act as electrolytes, ionic conductors. That is what the number one, ionic solids. It is formed by cations and anions. The fundamental particles are ions. Number two, it is covalent solids. Example, diamond. Diamond is a covalent solid where the fundamental particles are carbon atoms. So, atoms are the fundamental particles in covalent solids. Example, diamond. Carbon atoms arranged in a regular repeated network solid form. That is covalent solid. The atoms are fundamental particles. In ionic solids, ions are fundamental particles. In covalent solids, atoms are fundamental particles bound by covalent bond. The force of attraction is covalent bond. Generally, they are very hard with a high melting point. Generally, they are very hard with a high melting point and act as insulators. Like diamond, all of you know, the naturally available most hardest material is diamond, like that. At the same time, there are few exemptions like graphite, which maintain low melting character, soft in nature. At the same time, they can conduct electricity also. Hope you understand. There are few exemptions like graphite. So generally, covalent solids are extremely hard and they don't conduct electricity. They have high melting point. Coming to the third category, molecular solids. The fundamental particles are, as the term indicates, molecules. Fundamental particles are molecules. And based on the force of attraction, we know molecules, the force of attraction will be intermolecular forces of attraction. There will be three categories. What are the three categories? Number one, called polar molecular solids. Like example, HCl, there is polarity. Polar molecular solids. Number two, non-polar molecular solids. Example, if you take carbon dioxide is a non-polar molecule having dipole moment equal to 0. Solid carbon dioxide will be non-polar in nature, while the third category is hydrogen bonded in nature. Hydrogen bonded solids. It may be like HF, it may be like H2O, it may be like ammonia, where there is a possibility of hydrogen bonding given by the most electronegative fluorine connected to hydrogen. Second most electronegative oxygen connected to hydrogen. The third most electronegative nitrogen binding with hydrogen. Such molecules are able to perform hydrogen bonded character. So there are three variety of molecular solids maintaining polar molecular solids, where the molecules are polar in nature, where the force of attraction will be dipole-dipole attraction. Second one is non-polar molecular solids. There the force of attraction will be London forces. weak dispersion forces, and the third one, extreme strong variety of polar bonding, that is hydrogen bonded, given by hydrogen in a molecule, hydrogen connected to fluorine, hydrogen connected to oxygen, hydrogen connected to nitrogen. Respectively, the most electronegative fluorine, second most oxygen, third most nitrogen. So there are three varieties. They are generally soft in nature. Molecular solids are generally soft in nature, low melting in nature. They may not appreciably conduct electricity. Right? And the last one is metallic solids. Metallic solids are basically metals and ions. Metallic solids are basically metals and ions. There will be metal atoms surrounded by free electrons. Metal atoms are surrounded by free electrons. We call it as electron cloud or electron sea. Due to the presence of free electrons, all of you know, they are excellent conductors of heat and electricity. They are sonorous in nature. They are lustrous in nature. All of you know these facts. They conduct a good amount of electricity. They are good conductors of heat and electricity. They are sometimes hard materials. Heavy metals are hard in nature, while lighter metals like alkali metals, alkaline earth metals, they are relatively softer in nature. These are the four important types of solids: ionic solid, covalent solid, molecular solid, polar, non-polar, hydrogen bonded, and metallic solids. Next is on to the details of crystallography. Coming to the details of crystallography, we need to learn the term what is meant by lattice point. What is meant by lattice point? All of you know what is meant by space lattice. Space lattice. What is meant by unit cell, etc. Unit cell dimensions. It goes like that. Lattice point, space lattice, unit cell, etc. If we go through the NCERT, these are the points which we have gone through so far. Introduction area, characteristics of solids, crystalline amorphous, their features. This is the isotropy, anisotropy, various characteristics of crystalline and amorphous. It goes like that. Now, types of solids, molecular solids, ionic solids, metallic solids, covalent solids, a detailed talk on diamond, graphite and its molecular conditions, and a detailed discussion about the classification of solids with examples and properties. Coming to crystal systems, I can tell you this is the crystal system which we are learning now or which we are talking just now. And this is called a lattice point. All of you are aware of. This is called a lattice point. Lattice point. A point where a particle is assigned is called a lattice point. A point where a particle is assigned is called a lattice point. And the distribution of lattice point like this we call it as space lattice. The entire system we call it as space lattice. And in that space lattice, you can see one of the unit is given shaded. That is called a unit cell. What is meant by unit cell? All of you know. The regular repeated unit is called a unit cell. The building blocks of crystals is called a unit cell. The fundamental unit which keep on repeating in 3 dimension, building a crystal, is called a unit cell. Unit cell is the smallest arrangement unit. This is called a unit cell. This is called a unit cell. All of you know these things. And now a unit cell is categorized by or characterized by unit cell parameters. These are the unit cell parameters. The parameters include a lengthwise parameter A to B, that is A. Then this is a lengthwise parameter from this point to this, that is B, and height, this to this, that is called C. So length, breadth, height. Length, breadth, height, 3-dimensional parameters. You can consider like length, breadth, height, like that. So A, B, C, these are the lengthwise parameters concerned for a unit cell. While corresponding angle are concerned, you can find opposite to A, alpha, only convention, opposite to B, beta, and opposite to C, gamma. So a unit cell is characterized by 6 parameters basically, 3 lengthwise parameters and 3 angle parameters, A, B, C, alpha, beta, gamma. A, B, C, alpha, beta, gamma, based on which there are 7 fundamental crystal systems. We are learning 7 fundamental crystal systems based on the nature of the unit cell parameters. What are the 7 fundamental crystal systems? Fundamental crystal systems. There are 7 fundamental crystal systems. They are you can memorize like this. C. Tom Hart. You can memorize like this. C. Tom Hart. Hart in the SMS format. Okay. C. Tom Hart. Hart in the SMS format. C for cubic system. T for tetragonal system. O for orthorhombic system. And M for monoclinic system. And H for hexagonal system. R for rhombohedral system, also called a trigonal system, and T for triclinic system. Triclinic system. So cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, triclinic. These are the 7 fundamental crystal systems. All of you know that, right? They are characterized by the ABC parameters and angle parameters. For example, for cubic system, it is A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degree. The most symmetric system is cubic system. Most symmetric system is cubic system. ABC length, breadth, height are equal. Alpha, beta, gamma are equal and equal to 90 degree. All length, all angles are equal. All length are equal, all angles are equal and it is 90 degree. That is the most symmetric cubic system. What about tetragonal system? It is A not equal to B equal to C. A not equal to B equal to C. Or it may be better to be called as A equal to B not equal to C. One parameter will be unequal. A equal to B not equal to C. Okay, like that. Where the angle parameter remain dicto, same. Now orthorhombic system, it is A not equal to B not equal to C, while angle parameter remain the same. Right? Now monoclinic system. Monoclinic system, it is A not equal to B not equal to C. A not equal to B not equal to C, or rather it is repeating. We can verify that. Crystal systems are given. Cubic you see A equal to B equal to C. This one, and including examples it is given. Including examples it is given. You must go through thoroughly this table and by heart it. Because there can be a question giving the dimension, asking for which system it is, giving a system, what is the dimension, with examples they can ask you questions. You see tetragonal, A equal to B not equal to C, A equal to B not equal to C, this remains same, A not equal to B not equal to C, length, breadth, height are different, alpha, beta, gamma equal to 90 degree. You can imagine a matchbox. Length, breadth, height are different and alpha, beta, gamma are 90 degree. Now on to monoclinic system. It is A not equal to B not equal to C, where alpha, gamma 90 degree, beta not equal to 90 degree. A not equal, this repeat. It is better to memorizing purpose. You can give it a dicto. This will repeat. Okay. And here it will be alpha, gamma 90 degree, while beta not equal to 90 degree or not equal to 120 degree. Now coming to hexagonal system, it is A equal to B not equal to C. This will repeat. A equal to B not equal to C, where alpha equal to beta equal to 90 degree, while gamma is 120 degree. That is hexagonal system. While rhombohedral, it is A equal to B equal to C. This is going back. While alpha equal to beta equal to gamma, but not equal to 90 degree. This you can memorize with this. You see, A equal to B equal to C, alpha, beta, gamma equal. Equal to 90 is cubic, while A equal to B equal to C, alpha, beta, gamma equal, but not 90 degree. That is rhombohedral or trigonal system. And now the last one, most unsymmetrical crystal system. It is triclinic system. A not equal to B not equal to C, alpha not equal to beta not equal to gamma not equal to 90 degree. The most unsymmetrical crystal system, that is triclinic system. This is the most symmetrical, this is most unsymmetrical. A equal to B equal to C, alpha beta gamma equal to 90 degree. A equal to B not equal to, inequality starts. A equal to B not equal to C, this is same. A not equal to B not equal to C, this is same. This will repeat, while here this you need to by heart. Alpha gamma 90, beta not equal to 90. Then it is going back. A equal to B not equal to C. Alpha beta, this you need to memorize. Alpha beta 90, gamma 120. Now this you can correlate. And this is most unsymmetric. This is most symmetric. This is most unsymmetric. A, B, C are different. Alpha, beta, gamma are different. Not equal to 90 degree. The most unsymmetrical crystal system. Remember, you need to memorize the examples including all examples. For example, potassium dichromate. You must remember it is triclinic system. Blue vitriol, it belongs to triclinic system. Boric acid, it belongs to triclinic system. While graphite belongs to hexagonal system, diamond belongs to cubic system, not given, diamond. Diamond belongs to cubic system, while graphite belongs to hexagonal system. Like that, as much as possible, you need to go through the examples including, because with the example, they can ask a question. Hope it is clear. Now, that is the 7 fundamental crystal systems. Now, there are 4 types of arrangement. The crystal systems are available in 4 different types. What are the 4 different types? You can see this one. 4 different types. Type 1, type 2, type 3, type 4. Type 1 we call it as primitive system, also called symbol system. All of you know, particles coming only in the corner. That is primitive system. Only particles will be in the corner. That is primitive system. What about the other one? This is called the end-centered system. Particles are at corners as well as in any 2 opposite phase centers. You see, particle 1, 2, 3, 4, 5, 6, 7, 8 in the corners and 2 particles coming in the opposite phase centers only. That is called the end-centered system. Here how many lattice points? 8. Here how many lattice points? 8 plus 2, 10. Okay. And the third one, body-centered system. How many lattice points? There are 8 particles at the corner and 1 particle in the body center. 9 lattice points per unit cell. And the last one, face-centered system. What is a face-centered system? There are particles at corners and there are particles at each center of the face. You can see a particle in the top face center, bottom face center, left face, right face, front face, back face. There are 6 faces. All face centers, there are particles. How many lattice points? 8 at the corner and 6 in the face centers. 8 plus 6. 14 lattice points are there. Here you have 8 lattice points. Here you have 8 plus 2, 10. Here you have 8 plus 1, 9. Here you have 8 plus 6, 14 lattice points. Is it clear? Now, each crystal system available with each type of fundamental crystal system performing which all type of crystal systems present. That also you must understand. For example, if you take up cubic system, you can see only 3 types. Primitive is there, body-centered is there, face-centered is there. You have primitive, body-centered and face-centered. That is available for cubic system. What about a tetragonal system? There is only 2 types, primitive and body-centered. Primitive and body-centered available for tetragonal system. And the hero of the show is orthorhombic system. All 4 types are present for orthorhombic system. All 4 types. There is primitive, there is body-centered, there is face-centered, and there is end-centered. All 4 types are present for orthorhombic system. What about monoclinic? For monoclinic, you have only two types, primitive and end-centered system. You have primitive and end-centered system for monoclinic, while the rest all, only primitive is present. Only primitive is present for rest all. So for cubic system, there is primitive, simple cubic system, body-centered cubic BCC and face-centered cubic FCC. While tetragonal, primitive and body-centered. Orthorhombic, all four types are present. Primitive is there, body-centered there, face-centered there, end-centered there. And monoclinic, primitive and end-centered. The remaining all three, you have only primit. And if you take an account, you can see there are 14 crystal systems, maybe you are remembering. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 crystal systems you have, which you call it as Bravais lattices. Bravais lattices, there are 14 crystal systems available. Bravais lattices, 3 from the cubic system, 2 from the tetragonal system, 4 from the orthorhombic system, 2 from the monoclinic system, 1 each from hexagonal, rhombohedral and triclinic. 14 crystal systems called Bravais lattices. Is it clear? Our next point of discussion is regarding calculating the number of particles per unit cell. Calculating number of particles per unit cell. Calculation of number of particles per unit cell. You can also call it as rank of unit cell, represented as Z. Rank of unit cell. How to find the rank of unit cell? Basically, the important crystal systems. Most crystal systems that we are learning is cubic system. Let's have a look at the major cubic systems. How to find the rank of crystal systems? If you take up the simple cubic system, if you take up a simple cubic system, this is primitive cubic system. The contribution of particle in the corner is, all of you know, 1/8 contribution. This particle contribution is 1/8 contribution. You see the three diagrams. This is open model, this is space filling model, and this is actual contribution. Actual contribution, right? You know the particle present in the corner, it belongs to 8 unit cells. So what is the contribution to 1 unit cell? It is 1/8 contribution. So how many particles per unit cell effectively? It is 1/8 into 8 equal to 1. So rank of primitive system, it is 1. All of you know that. I'm just reminding you. What about body-centered system? What is the rank for body-centered system? For a body-centered system, this is body-centered system. What is the rank coming? There are particle at the corners. All of you know it is 1/8 contribution. While the particle in the body center, it is 1 full contribution. So what is the rank? Naturally, 1/8 into 8 equal to 1. And 1 plus 1, 2 is the rank. Rank for BCC, it will be 2. Rank for primitive system, 1. Rank for BCC, 2. What about rank for FCC? What is the rank for FCC? How much it is coming? Rank for FCC. This is face-centered system. This is FCC, face-centered system. There are particle at corners. It is 1/8 contribution. And a particle in the face center, it is half contribution. A particle present in the face center, it belongs to 2 unit cells. 2 unit cells when combined, that's a particle coming in the face center. So this particle which is in the face center, you can see this is the face center position. The half particle belong to this and half particle belong to the other unit cell. So it will be half contribution. So how comes the calculation? 1/8 into 8 equal to 1, and half into how many faces? Left, right, top, bottom, front, back. So it will be 6 faces. So it will be 3 particle, 3 plus 1, 4 is the rank. Rank of the FCC will be 4. Right? So simple cubic system, rank is 1. Body-centered system, rank is 2. Face-centered system, rank is 4. Right? What about end-centered system? Not given in the text. What about end-centered system? This is end-centered system. Already we have learned. The particles are coming at a corner. as well as the particles are coming at two opposite phase centers. What will be the rank? Corner contribution will be 1 by 8 into 8 corners, 1 contribution, and phase center contribution, it is half, and only 2 phases, half into 2, 1. So it is 1 plus 1, 2 is the rank. Rank for end-centered system will be 2. So primitive system, rank is 1. Body-centered system, rank is 2. Face-centered system, rank is 4. How 4? 3 plus 1. Okay. 1 in the corner, 1 by 8 into 8 equal to 1. And face centers, half into 6, 3. Agreed? Now, what about end-centered system? Rank is 2. 1 plus 1. This is how you find the number of effective particle per unit cell. That is called a rank. Please understand, a particle coming at a corner, contribution will be 1 by 8. A particle coming in the body center, contribution is 1. A particle coming in the face center, contribution is half. A particle coming in the edge center, that is not coming in this discussion. Suppose there is a particle coming in this edge center. Imagine there is a particle here. The contribution is 1 by 4 contribution, because one edge is common for 4 unit cells. So the contribution will be 1 by 4 contribution. So corner, 1/8 contribution. Body center, 1 contribution. Face center, half contribution. And edge center, 1/4 contribution. Is it clear? That's about calculation of effective particle per unit cell, so called rank. Next topic is close packed arrangements. Next topic is close packed arrangements. You see, this is the close packed arrangements. Particles arranged in a line. This is one-dimensional array. This is called a one-dimensional, 1D, one-dimensional array. It is one-dimensional array, particles aligned in a line that forms the edge of a crystal. That forms the edge of a crystal. While particle can be arranged forming a layer, this is one layer. It can be 2 types of arrangement. This is two-dimensional array. There can be 2 types. One is called the square close packing. Square close packing in 2D, and this is hexagonal close packing in 2D. Square close packing in 2D, hexagonal close packing in 2D. Here you can find the particles are vertically and horizontally in a line. Particles are vertically and horizontally in a line, and one particle is in contact with the 4 particles surrounding, forming a square. That's why it is called a square close packing, and hence the coordination number will be 4. What is meant by coordination number? Coordination number. Coordination number means number of particle one particle is in contact with. How many particle one particle is in contact with? That is called a coordination number. You can see this one particle shaded is in contact with this. Coordination number is 4. Meanwhile, coming to this, you can see there is a horizontal alignment. While vertically, the alignment is between first and third layer. First line and third line particles are vertically aligned, while the second line particles in the depressions of the first. The second line particles are in the depression of the first. The arrangement so comes like one particle is in contact with the 1, 2, 3, 4, 5, 6 particles. What is the coordination number? Here the coordination number is 4. Here the coordination number is 4. What is the coordination number here? 6 is the coordination number. Okay. So particles aligned in a line, one-dimensional array that forms the edge of a crystal. Particles arranged in a surface, two-dimensional array, square close packing and hexagonal close packing. Square close packing coordination number 4, hexagonal close packing coordination number 6. Agreed? Now it is 3D arrangement. 3D arrangement. How comes the 3D arrangement? Let's have a look at. How comes the 3D arrangement? This is one 3D arrangement. We call it as AAAA packing. AA arrangement, AA packing arrangement. In AA packing arrangement, you can see this particular arrangement is repeated. The previous one which we have seen, this layer is taken and put one over the other. We are taking this layer. We are taking this layer and put one over the other. That is what we do. Look at this layer. Since it is diagrams, it will take time. You see, this layer is taken and each layer put one over the other. That forms the AAAA type arrangement. That forms a simple cubic system. This is a simple cubic system. AAAA pattern, 3D pattern. It's so-called AA pattern. It take time for make it, but yeah, exactly. You can see that. This is AA packing simple cubic lattice. This is simple cubic lattice. If you look at the arrangement, you can find it forms particle coming at the corners. Only in the corner. This pattern is repeating. This pattern is repeated over here, and this is called a simple cubic system. Simple cubic system. What is the coordination number of simple cubic system? What is the coordination number for simple cubic system? Very simple to understand. If you take one particle, it is in contact with a 1, 2, 3, 4. Okay. Now, behind this particle, there is one particle in contact. So, 5. In front of this particle, there is one particle in contact. You please assume 3D. 3D. You can see 4 particles in contact now. Behind this particle, there is a one particle in contact. In front of this particle, there is one particle. So, total 6 is the coordination number. Coordination number will be 6. So, 4, what do you see here? One behind, one in front. That will be in contact. 6 particles are in contact with the one central particle. Coordination number will be 6. So, this is one type of 3D arrangement. Okay. While the other 3D arrangements are very important, that is called AB packing and ABC packing. AB packing and ABC packing. This is what the arrangement is. AB packing and ABC packing. First of all, let's have a look at AB packing called hexagonal close packing, HCP. This is layer A. Hope you understand the cross-sectional view of layer A. This is layer A. Cross-sectional view of layer A. Over the top, layer B. This is layer B. The 3 particles. We are representing one unit arrangement. Okay. So, layer A, layer B, then layer A. Layer A, layer B, then layer A, then layer B. It repeats. That is what called hexagonal close packing, AB packing. It is called AB packing. AB packing. This is AB packing. Okay. Hope you understand. What is the coordination number? What is the coordination number? For example, this one particle in contact with how many particles? This one particle in contact with how many particles? 6 particles in that layer, 6 particles in that layer, and 6 particle in that layer, 3 particle below and 3 particle above. So it is 6 plus 3 plus 3. 12 is the coordination number. One of the highly effective close packed system in 3D. HCP. And this is the open structure of HCP. Open structure of HCP. Is that clear? Right? And now another arrangement is cubic close packed arrangement. This we call it as AB packing. AB recurring pattern. This is called ABC pattern. ABC pattern. ABC pattern. What is ABC pattern? There is layer A, and there is layer B, and then there is layer C. Layer B and C are just opposite. Layer B and layer C are just opposite. Layer B like this, layer C like this. Layer B, if it is like this, layer C will be like this. just opposite, reversed one. So layer A, layer B, layer C, layer A. A, B, C, A, B, C recurring pattern. That is called the cubic closed packed system, CCP. Cubic closed packed system, CCP, also called FCC. FCC and CCP are same. FCC and CCP are same. ABC pattern. What is the coordination number in this case? What is the coordination number in this case? Very simple to understand. How many particles this is in contact with? 6 particles in that layer and 3 particles below and similar 3 particles above. So it is again the same thing. 6 plus 3 plus 3. 12 will be the coordination number. The packing efficiency, coordination number, everything will be same. But the arrangement is different. In HCP, it is layer AB pattern. It will come like a hexagonal system. While FCC, that is CCP, cubic closed packed system, it is ABC pattern. It will go for a CCP arrangement, FCC arrangement, cubic system. It makes a cubic system. This is the cubic system. Okay. Both are equally efficient packing. They are the most important pack. You can see the FCC arrangement here. You can see the FCC. Layer A, layer B, layer C. I told you B and C are opposite layers. Don't you understand? B and C are opposite. B and C are opposite. If one is like this, one is like this. Okay. Now A, B, C, A, it repeating. You see A, B, C, A. And this arrangement already we have seen. Where it was seen in the FCC arrangement, face-centered cubic system. This is face-centered cubic system. Particle at corners. And each particle in the center of the face. Top face, bottom face. Left face, right face. Front face, back face. So this is, you see this arrangement. This is layer A, this is layer B, and this is layer C, and this is layer A, like that. FCC, face-centered system, also called a CCP. So which are all the basic closed packed systems? One-dimensional array forming a line, two-dimensional array forming a surface, square closed packing, and hexagonal closed packing. Right? Then cubic system. Symbol cubic system, A pattern symbol cubic system, then AB pattern HCP, then ABC pattern CCP. Okay, fine. Now regarding the voids. Now regarding a talk on voids. Voids means the vacant space in between the crystals is called voids. The vacant space between the crystals is called voids. Voids are vacant spaces. If you take 3 particles like this vacant space is called a triangular void. Triangular void. That is in 2 dimensions. If you take 4 particles like this, there is a vacant space over here. That is called a square void. That is also in 2D. This is also in 2D. While if you take a system like this, triangular void, square void, if you take a system like this, that is symbol cubic system, there can be a void. If you take this one, this is a symbol cubic system. This is a symbol cubic system. Hope you find a void here. In between 8 particles, there is a void. In between these 8 particles, here there is a void. That is called a cubic void. Cubic void. So there is triangular void in 2D. There is square void in 2D. There is cubic void in symbol cubic system. While the other 2 are, so that is cubic void. That is about the cubic void. I am not drawing cubic void. The other 2 important voids are tetrahedral void and octahedral void. They are most important in the 3D closed packed arrangement. Tetrahedral void and octahedral void. How comes the tetrahedral, octahedral void? Pictorially, you can understand this is the tetrahedral, octahedral void. See, tetrahedral void is formed in between four particles. You see the four particles, particle 1, 2, 3, and a fourth particle placed over here. Four particles arranged like this. This void is called a tetrahedral void. It is available in between four particles, 1, 2, 3, 4. Somewhere in between is tetrahedral void, observed in close packed systems. While octahedral void means you have three particles like this, for example, layer B and layer C, opposite layers, three particles like this. Place these three particles over the top like this. This void is called the octahedral void. It is between six particles. 1, 2, 3, 4, 5, 6. Between six particles, there is octahedral void. Between four particles, there is tetrahedral void. Is it clear? It is observed in close packed arrangements. Close packed arrangements. Imagine in a close packed system. Imagine in a close packed system, if there are n particles. In a close packed system, if there are n particles, then number of tetrahedral voids is equal to 2n and number of octahedral voids is equal to n. And total voids will be 3n. So if there are n number of effective particles in a close packed arrangement, the number of tetrahedral voids will be 2n. Number of octahedral voids will be n. For example, if you take an FCC system rank equal to 4, that means number of particle equal to 4. Number of tetrahedral void will be 2n, it will be 8, and number of octahedral void will be n, that is equal to 4, and total voids will be 8 plus 4, 12 voids will be present. Is that clear? Is that clear? Yes. And those voids in a closed packed arrangement, you can visualize over here. You can visualize the tetrahedral, octahedral voids over here. Between six particles, you can find the octahedral void. Between six particles, you can find the octahedral void. Hope you see the six particles. You see octahedral void observed in six particles. 1, 2, 3, 4, 5, 6. Between six particles, you will find octahedral void. While between four particles, you can find tetrahedral void. T will be found between four particles. You will find the four particle giving tetrahedral void. What are the four particles? You see this 1, 2, 3 and 4. Between four particles, you will find a tetrahedral void. Between six particles, you will find a octahedral void. Which is greater in a number? Simply count and see which is greater in number, tetrahedral void or octahedral void. Which one you find greater in number, T or O? Very simple. T is greater in number because for each particle there will be 2 tetrahedral void and there will be 1 octahedral void in a closed packed system. Is that clear? Right. Now our discussion is on unit cell dimensions, unit cell parameters and its packing efficiency. Packing efficiency is our discussion next. Packing efficiency. Packing efficiency. How to find the packing efficiency? Packing efficiency is equal to volume of particle in a unit cell divided by volume of unit cell into 100. This is packing efficiency. You need to practice simple cubic system and you need to practice body centered system and you need to practice face centered system. Simple cubic system, body centered system, face centered system. Okay. First of all, let's have a look at simple cubic system. How to get the simple cubic system? This is simple cubic system. There are particles at the corners only. Okay. So volume of the particle, packing efficiency is equal to volume of the particle. How to get the volume of the particle? How many particles are there? It is 1 by 8 into 8. There is one particle. So one particle I am taking as sphere 4 by 3 pi r cube. Assuming the particle radius to be r. Assuming the particle radius to be r, there is one particle effectively available. It is 4 by 3 pi r cube divided by edge length of the cube. Let it be a. Edge length of the cube. Let it be a. It is a cube into 100. Right? Now, if you get the relation between a and r, you get the final figure. What is the relation between a and r? Hope you understand from this point to this point. Actually, particles are in contact. We are drawing the open structure. This is A. This is A. And it is 2R. A is equal to 2R. So what do you get? 4 by 3 pi r cube divided by 2R the whole cube. That is what the point. So how much you get? How much you get? 4 pi r cube 3 into 8 r cube, isn't it? 8 r cube, 2 raised to 3, 8 r cube cancels. So how much you get? It is 2, you get pi by 6, that is the figure, pi by 6, that is the packing efficiency is pi by 6 into 100. You will get 52 percentage. You will get 52 percentage something. That will be the packing efficiency of primitive system. Packing efficiency of primitive system. Where is packing efficiency? Yeah, 52.4 percentage. That is the packing efficiency of primitive system. Is it clear? How to get that? Volume of the particle. Volume of the particle divided by volume of the particle divided by volume of the unit cell into 100. How many particles are there? At the corners, 1 by 8 into 8. One particle. What is the volume? 4 by 3 pi r cube. Assuming to be spherical with radius r. Divided by volume of the unit cell. It is a cube. What is the relation between a and r? A is equal to 2r. So 2r the whole cube. 4 by 3 pi r cube by 2r the whole cube. You will get pi by 6. Remember this terminology also. Sometimes that may be presented as a choice. Okay. Next one, it is BCC. How to work out for BCC? How to work out for BCC? This is BCC system. All of you know. There is particle at the corner and particle in the center of the body. Particle at the corner and particle present in the center of the body. Right? So, the edge length of the unit cell given A and particle radius given R. Now once again, packing efficiency equal to volume of particles divided by volume of unit cell into 100. So what is the volume of the particle? It is 2 into 4 by 3 pi r cube. How it is 2? There is corner particle. The rank is 2. For BCC, rank is 2. Corner particle 1 by 8 into 8 equal to 1. And body center particle 1. 1 plus 1, 2. 2 into 4 by 3 pi r cube divided by a cube. Now we need to get a relation between A and R. How to get the relation between A and R? You can take the body diagonal. Body diagonal AB. Body diagonal AB is equal to root 3A. All of you know what is the body diagonal of a cube. Body diagonal of a cube having edge length A will be root 3A. Right? Root 3A. And now how these three particles are available? They are in contact. Particle 1, particle 2, particle 3. They are in contact. And this distance is AB distance. This distance is AB distance. And that is root 3A. It is R, 4R. So root 3A is equal to 4R. A is equal to 4R by root 3. A is equal to 4R by root 3. So it will be 2 into 4 pi r cube divided by 3 into 4r by root 3. 4r by root 3, the whole cube. Right? So how much you get? How much you get? 2, 4, pi, r cube, root 3 whole cube will go to top. That will be 3 root 3. Root 3 whole cube divided by 3 into 4, 4, 4 into r cube gets cancels. So 1 4 will get cancelled. Then this also will get cancelled. This 3 will get cancelled. How much you get? Root 3 pi by 8, isn't it? It is root 3 pi by 8. Am I right? Please verify. Root 3 pi by 8, 4 into 2, 8. Root 3 pi by 8. Which when you work out, you will get 68 percentage. Which when you work out, you will get 68 percentage. 68 percentage. It will be root 3 pi by 8. Root 3 pi by 8. Is that clear? Fine. So primitive system, pi by 6, that is 52%, and body centered system, root 3 pi by 8, that is 68 percentage. Now it is FCC system. FCC. How comes FCC? FCC is particles at the corners, and particles in the center of the faces. Top face, bottom face, left face, right face, front face, back face. This is what the arrangement of particle. Imagine the edge length given, it's A, and the particle radius given R. Once again, packing efficiency equal to volume of particles divided by volume of unit cell into 100. What is the volume of the particle? 4 into 4 by 3 pi r cube. By 4 for FCC, rank equal to 4. How it is the rank 4? Corner particle 1 by 8 into 8 equal to 1. And the face center particle, it is half into 6 equal to 3. 3 plus 1, 4. So 4 particles are there. 4 into 4 by 3 pi r cube divided by a cube. Here what is the relation between A and R? Here the A and R relation you can get from the face center. Look at the face center and look at the face diagonal. This is face diagonal. Suppose you are taking AB, that is face diagonal. Face diagonal, all of you know, for a cube, face diagonal AB is equal to root 2A. And here 4 particles are available like this. Sorry, 3 particles are available like this. This is AB distance. This is AB distance, which is root 2A, face diagonal. Root 2A equal to R plus R plus R plus R. 4R. Root 2A is equal to 4R. A is equal to 4R by root 2. Okay, substitute here. You get 4 by 3 pi r cube. A how much? A how much? 4r by root 2. 4r by root 2 the whole cube. So how much it is coming? 4 pi r cube root 2 cube. It will be 2 root 2 divided by 3 4 cube. 4 cube into r cube. R cube will cancel. 4 cancels, and this 2 with this cancels. You get root 2 pi by 6. You are getting root 2 pi by 6. When converted to percentage, you will get 74 percentage. You will get 74 percentage. When converted to percentage, you will get 74 percentage. You will get root 2 pi by 6. Root 2 pi by 6. Right? So these packing efficiency you need to review. Simple cubic system, body centered system, face centered system, packing efficiency, and dimensional parameters you need to review. Is it clear? Fine. And now the next topic is density of the crystal. density of the crystal. That's an important topic. Density of the crystal. You can expect numericals from this part. Density, all of you know, it is mass by volume, and the formula for density of the crystal, D is equal to Zm by NaA cube. This is the density formula. Zm by NaA cube. What is Z? D is density. What is Z? Z is the rank of the system. What is rank for primitive? 1. Rank for BCC? 2. Rank for FCC? 4. What is M? Molar mass. What is Na? Avogadro number. What is A? Edge length. If we are dealing with the cubic system, A equal to B equal to C, and the volume will be A cube. This is nothing but volume. So this is nothing but mass of a unit cell. Zm by Na is mass of one unit cell. A cube is volume of the unit cell. Mass by volume, density. Okay. Or you may be encountering a formula like this. Zm by N into A cube. Now, what is this M? Molar mass. This is Avogadro number. What is this M? A given mass. And what is this? Number of particles in that mass. So, if in the numerator it is molar mass, denominator it will be Avogadro number. If it is a given mass in the numerator, in the denominator it is the number of particles in that mass. So, this is nothing but number of particles present in m gram. This is Avogadro number, this is molar mass. Hope you understand. Is it clear? That is the important points regarding crystallography and its calculations. Right? Next, the last topic of the chapter is regarding crystal defects. Crystal defects. That is the last topic from the chapter. Crystal defects. Imperfections in crystals. Imperfections in crystals. Mainly we are discussing point defect. These are stoichiometric point defect. Stoichiometric point defect. There are two types of defects. Basically three types. Stoichiometric defect, impurity defect, non-stoichiometric defect. What is stoichiometric defect? The one do not disturb the formula. A crystal defect which does not disturb the formula is called a stoichiometric defect. Then what is non-stoichiometric defect? The one which disturbs the formula is called a non-stoichiometric defect. Right? Let's have a look at various defects. This is one vacancy defect. This is called a vacancy defect. Simple to understand. Some particles are missing. Here one particle missing. That is called a vacancy defect, which definitely will cause a decrease in density of the crystal. Density of the crystal will decrease. Okay, that is vacancy defect. And this is interstitial defect. Look at the defect. There are particles available in the vacant spaces. In the previous case, the particles were missing. Here, particles are available in the vacant spaces. That is called the interstitial defect. Interstitial defect. While two important defects are Schottky defect and Frankel defect. Here, the density will increase. Okay. These are the two important defects all of you know. Schottky defect and Frankel defect. Schottky defect and Frankel defect. Have a look at Schottky defect and Frankel defect. Number one, Frankel defect. What is observed in Frankel defect? There are some particles misplaced. That is Frankel defect. You see the arrangement of cation, anion. It is observed in an ionic crystal. You can see the arrangement of cation, anion. Anion, cation, anion. This is supposed to be the location of a cation, but that is missing. And that cation is available somewhere in the interstices. That cation is available somewhere in the interstices. You see the cation available here. The cation that was supposed to be here is available here. It is misplaced. It's a dislocation defect. Okay. Whenever the cations are very small, this kind of defect is observed. We find some ions are missing from its original point and found to be available in the nearby void. That is called a Frankel defect. There is no density change because no particles are missing. It is only misplaced. Okay. One Frankel defect is equal to 2 defects. One is it is not observed available in the observed available location. One is where the expected particle is, there is no particle. Number one. Number two, where we don't expect a particle, there is a particle. Hope you understand. So a cation, a small cation expected to be here but not available there. Actually it is misplaced. Such defects are called dislocation defects, Frankel defect. While Schottky defect means missing of equal number of cation anion. That is Schottky defect. Whenever the size of cation anion are comparable in nature, we find a Schottky defect. Whenever the ionic size is largely differing, we find a Frankel defect. Whenever the ionic sizes are comparable like NaCl, we find a Schottky defect. Look at this area. Anion, cation, anion, cation. Here we expect a cation, but that is missing. Here we expect an anion, that is missing. So missing of equal number of cation anion leading to Schottky defect. Schottky defect is a prominent defect observed in crystal like NaCl. Crystals like NaCl, Schottky defect is prominently observed. There are certain observed data is given which you can find in the Ncert since diagrams are available. You see, some data is commented there. In NaCl, there are approximately 10 raised to 6 Schottky pairs per centimeter cube at room temperature. That is, in 1 centimeter cube, there are 10 raised to 22 ions. There is 1 Schottky defect per 10 raised to 16 ions. That means it is significant defect. Okay, it is observed in crystal like NaCl, KCl, CSCl, AgBr, etc., where the size of cation anion are comparable. AgBr is to be specifically noted because AgBr is able to perform both the Frankel defect and Schottky defect. Is it clear? So vacancy defect, interstitial defect, Schottky defect, Frankel defect. Next is impurity defect. Next is impurity defect. This is what impurity defect. In a crystal like NaCl, when doped with some impurity like strontium chloride, you find Na plus Cl minus, Na plus Cl minus, Na plus Cl minus. You can see 2 places sodium is missing and at 1 place strontium is coming. Impurity defect. 2 sodium missing. 1 position occupied by strontium. You know strontium is divalent. So for 2 sodium, 1 strontium is enough to neutralize the charge. An ionic crystal must be electrically neutral. That's all. Is it clear? Now you see 2 sodium missing, 1 strontium comes and 1 position remain vacant. So number of vacancies will be equal to number of strontium present. Suppose there are 1 lakh strontium present, there are 1 lakh vacancies. There can be questions concerned to that calculations. Simple questions. Okay. That is impurity defect. Next is non-stoichiometric defect. There are metal excess defect and metal deficiency defect. Metal excess defect may be due to anion vacancies. This is metal excess defect due to anion vacancies. Imagine NaCl crystal is heated with the sodium vapors. NaCl crystal, all of you know, colorless. If you heat with the sodium vapors, it will turn yellow in color. The reason behind is, this is pure NaCl crystal when heated with the sodium vapors. Imagine this is heated with the sodium vapors. Some sodium atoms will be adhering to the surface. Some sodium atoms will be adhering to the surface. In order to compensate with that sodium, some anions will be, there was a chloride ion here. Some anions will be migrating to the surface. And Na becomes Na plus, losing electron, and that electron come and trap in the anion vacancy. I repeat, when sodium chloride heated with the sodium vapors, sodium atoms adhere to the surface. Okay. Now, some of the Cl minus migrate to surface where Cl minus vacancy will be created. In that created Cl minus vacancy, electron released from sodium will come and trap. It is called F center. Electron trapped centers are called F center, Farben center, causing color to the system. And that lead to the color formation. Now there is metal excess defect. Earlier, suppose sodium and chlorine, it was 100 available. Some of the chlorine go out. Now the new system will be 100 sodium and 90 chlorine. So it is metal excess defect due to anion vacancies, because some of the chloride migrate to the surface and that chloride missing creates a vacancy, and that creates an imbalancing between sodium and chlorine number, and sodium becomes excess, metal excess defect due to anion vacancy. In that anion vacancy, electrons get trapped and they act as coloring centers. We call it as F center. F center. Okay. Now the same thing can happen, metal excess defect due to extra cation. Metal excess defect due to extra cation. Suppose we are heating zinc oxide. Imagine we are heating zinc oxide. Zinc oxide, all of you know, it is 1:1 ratio. 100 zinc, there are 100 oxygen. When zinc oxide is heated, you can see some oxygen gas is released. Some oxygen atoms are escaping. So what will happen? There will be a reorganization in the crystal. Some oxygen atoms are escaping when you heat zinc oxide. What will happen is there will be a reorganization. Some oxygen is gone. Imagine 10 oxygen gone. Now it is zinc 100 and zinc oxygen 90. Some 10 oxygen atoms gone. Imagine. Now it is 190. This crystal will go for a reorganization. You make it 90-90 crystal. Now 10 zinc atoms are excess. Those excess zinc atoms which is created due to the escaping of oxygen, they will trap in the vacant sites. They will trap in the vacant sites, and the consecutive corresponding electrons will trap in the nearby vacant site, and they act as F centers. Remember, all ionic crystals must be electrically neutral. So I repeat, there was 100 zinc and oxygen. Upon heating, some 10 oxygen escaped. Now you get 190. Now this crystal reorganizes. You get 90-90 crystal and 10 zinc extra trapped into vacant sites, voids. And the corresponding electrons trapped in the nearby voids. And that void electron trapped act as F center, and the white powderous zinc oxide becomes yellow in color. Hope you heard about zinc oxide is called a philosopher's wool. According to change in temperature, there is a change in color from white to yellow, yellow to white, like that. It is due to crystal defects. Okay. So metal excess, this is metal excess defect, metal excess defect. Metal excess defect due to anion vacancy, metal excess defect due to extra cation. Next is metal deficiency defect. Metal deficiency defect. There are so many non-stoichiometric compounds. For example, ferrous oxide. We find it is 1:1 combination. Many times we can find it is iron 0.96, oxygen 1, like that. Non-stoichiometric compounds. We find metals to be deficit. Number of metal atoms found to be deficit. For 100 oxygen, there is only 96 iron. For 100 oxygen, there is only 96 iron. This is non-stoichiometric compounds, metal deficiency defect. And how these ionic crystals are maintaining the charge. See, now this is not balanced charge. Oxygen minus 2 into 100, minus 200. Iron 2 plus into 96, it will be plus 182. This is not balanced. How they maintain electrical neutrality? Think. Very simple. Some of the Fe2 plus will be converted to Fe3 plus, and thereby each conversion the charge increases by 1 unit. Thereby it can compensate the electrical neutrality. Thereby, it can maintain the electrical neutrality. You can expect problems based on that. Of course, we are going to do the problems in the class. Okay, that's all regarding crystal defects, right? Now, a topic on electrical conductivity. Electrical conductivity. Regarding electric properties, we have three types of material: conductors, which maintain conductivity 10 raised to 4 to 10 raised to 7 per ohm per meter. Electrical conductors. Insulators maintained electrical conductivity 10 power minus 20 to minus 10 per ohm per meter. Semiconductors 10 raised to 6 to 10 raised to minus 6 to 10 raised to 4 per ohm per meter. This is the band theory explaining conductors, semiconductors, insulators. According to band theory, every material there will be a filled electron band and there will be a conduction band. This is conduction band and this is filled electron band. A band means collection of orbitals. Band means collection of orbitals in the valence shell. So this is electron filled band. This is empty conduction band. Okay, the theory suggests the materials categorized into three varieties. Number one, the filled band and empty conduction band, they are far apart. You see, the electron filled band and empty conduction band, they are far apart. That means these electrons are not available here to make conductance. They are insulators. There is a large energy gap between filled orbital band and empty conduction band, unable to conduct electricity, act as insulators. While the next one, they are very close. You see, they are very close. There is only a small energy gap. So some of the electrons may be available here. They act as semiconductors. While for metals and alloys, they overlap. The conduction band and valence band overlap. Valence band and conduction band overlap. So there is a good amount of electrons available in the conduction band and they are very good conductors of electricity. They are conductors, metals, they are insulators and they are semiconductors, right? And in semiconductors, we improve the electrical conductivity by doping process. Hope you heard about doping process. You are learning that in physics and all. This is a doping process demonstrated in the Ncert. This is a perfect silicon atom having 4 valence electrons distributed in a perfect crystal, and that is doped with a higher group impurity like arsenic from group 15. Silicon belongs to group 14. So group 14 silicon containing 4 valence electron doped with a group 15 element arsenic containing 5 valence electron. There will be 1 electron extra. So that extra electron start electrical conductivity improvement, and that is called N-type semiconduction. You are learning better in physics. While the same perfect crystal doped with the boron impurity, that is lower group impurity. When higher group impurity added, there is extra electron coming, there is extra conductivity. When a lower group impurity is added, there will be a hole, electron deficiency. We call it as hole. And that gives extra conductivity. A hole can act as extra electrical conducting, and that is called a P-type semiconduction. This is N-type semiconduction. This is P-type semiconduction, as there is a electron deficit. Sir, how this electron deficit gives conductivity? You see, this is a hole to which this electron can jump. So the migration of electron will be accelerated with the presence of electron holes. Okay. So that will conduct electricity. That is called a P-type semiconductors. N-P semiconduction is very important in the electronic industry. I don't have to tell you. And the last topic is magnetic properties. Every material has got magnetic property. Every tiny electron can act as a magnet. Every electron can act as a tiny magnet, because an electron is associated with 2 types of movement. It is moving around the nucleus. There will be a magnetic moment. While it is spinning in its own axis, there will be a spin only magnetic moment, there will be a orbital magnetic moment. So there is a orbital magnetic moment, there is a spin only magnetic moment. Somehow the value is very low. It's a very low value measured in Bohr magneton, and the value is 9.27 into 10 power minus 24 ampere meter square. A very low figure. Okay. Now, the materials based on their magnetic property categorized into certain classes. All of you know regarding that: paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. What are paramagnetic materials? What are paramagnetic materials? Which are weakly attracted in a magnetic field due to the presence of unpaired electrons. Any system which contain unpaired electron create a weak force of attraction in the magnetic field and is called paramagnetic. Example, almost all transition metals are, their compounds are paramagnetic. O2 is paramagnetic due to the presence of unpaired electron in the antibonding pi star orbitals. All of you know that. Now, what about diamagnetic substances? Example, water, NaCl, benzene. Lot of molecules are diamagnetic in nature. Diamagnetic means all the electrons are paired. That is diamagnetic. They experience a weak force of repulsion when introduced into a magnetic field. That is diamagnetic. So weak force of attraction in the magnetic field, paramagnetic. A weak force of repulsion in the magnetic field called diamagnetic. Unpaired electron causes paramagnetism. All paired electron causes diamagnetic. What is ferromagnetism? A high degree of paramagnetism is called ferromagnetic. In ferromagnetic material, which are materials used for preparing permanent magnets, the magnetic dipoles are aligned in a unique manner. Magnetic dipoles are aligned in a unique manner. Magnetic dipole means a collection of a group of atoms act as a domain. A group of atoms act as a domain, and that domain giving a magnetic moment, it is aligned in a unique fashion, unique direction, all aligned in a unique direction when introduced into a magnetic field. So what? The magnetic attraction will be very high. Is that only? No. The magnetism character is retained. The magnetic property is retained. That's why they are used for preparing permanent magnets, iron, cobalt, nickel, etc. Iron, cobalt, nickel, gadolinium, CrO2, they are strongly attracting in the magnetic field. That is ferromagnetic. What about antiferromagnetism like MnO? Antiferromagnetism. Diagram B. You see the domains aligned in the magnetic field in such a way that one up, one down, one up, one down. They are arranged parallel, anti-parallel in opposite direction, so that their moments cancel each other. That is antiferromagnetism. Example, MnO. And the last one is ferrimagnetic, like Fe2O3 or Fe2O4. Ferrimagnetism, the magnetic domains are aligned in such a way that parallel, anti-parallel in unequal direction. So some will cancel, some will be retained. That is ferrimagnetism. Right? That is the magnetic property and their categorization. Paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. Is it clear? Ferromagnetic, all domains aligned in unique way. Maximum attraction. Antiferro means opposite, cancels. Ferri means parallel, anti-parallel in unequal direction, unequal numbers, so that some of the domains will cancel and some will retain. Right? This is the major discussion happening in the chapter. Let me remind you, we started from characteristics of solid, liquid, gas, crystalline, amorphous, characteristics of crystalline, amorphous, types of solids, ionic, molecular, covalent, metallic, unit cell, dimensions, 7 fundamental crystal systems, 14 Bravais lattices, calculating the rank, number of effective particle per unit cell, close packed arrangements, about voids, right? Close packed arrangements, one dimensional, two dimensional, surface, 3D, AAAA packing, AB packing, ABC packing, packing efficiency, density of the crystal, defects of the crystal, electrical properties, and finally magnetic properties. This is the chapter in NCERT. The coverage comes in the chapter crystallography, right? With this we wind up that discussion. We will meet in another class with another chapter. Okay, bye, see you, take care.